Okay, welcome back everyone. So this is video 11 of the series, and in this video we're going to consider various different ways in which we can separate the quasi-permissionless and the dynamically available settings. Okay, so in fact what we're going to do is establish three separations between the dynamically available and quasi-permissionless settings. Okay, so roughly, we'll just going to define these things in more detail in a bit. So the three separations as follows. So dynamically available protocols cannot function in the partially synchronous model, while proof-of-stake quasi-permissionless protocols can do so. Okay, we've already seen that dynamically available protocols can't, but later on we'll see that proof-of-stake protocols can function in the partially synchronous setting and the partially synchronous and quasi-permissionless setting. Dynamically available protocols can't be accountable, while quasi-permissionless protocols can be. That's our second separation. And our third separation is that dynamically available protocols cannot be optimistically responsive, while quasi-permissionless protocols can be. Okay, so we haven't yet defined what we mean by accountable. We haven't yet defined what we mean by optimistically responsive, so we'll define those things in a little bit. As already mentioned there, for the first separation, we already saw that dynamically available protocols cannot function in partial synchrony. Okay, and later on, we'll see that quasi-permissionless proof-of-stake protocols can. Okay, so that'll give us the first separation. For the second separation, right, first of all, we need to define accountability. Okay, so let's do that next. So intuitively, a protocol is accountable if there's always a smoking gun for consistency violations, right, such as two signatures by a common identifier that support conflicting transactions. So formally, we adopt the definition of forensic support by Sheng et al. Okay, they studied the traditional permission setting without external or on-chain resources. We now have to adapt things to the quasi-permissionless setting, and that makes things a little bit complicated because now we have stake and resources changing hands. Okay, and you'll see that makes things, some of the definitions, a little bit more complicated. Okay, so how do we define accountability? Well, consider a blockchain protocol sigma OC. So I don't want you to worry too much about notation here because in these talks I haven't gone into all the details of the paper. I haven't properly explained all the notation we use in the paper. Basically, sigma here is just a state machine diagram that specifies how honest players should behave when executing the protocol. O is just a set of permitters, and C is your notion of confirmation. It determines when transactions should be considered confirmed. Okay. So anyway, consider a blockchain protocol and some security parameter epsilon. Okay, for a player set P and a set of identifiers ID star, let PID star be the obvious sort of thing. It's just the players in P that own one of the identifiers in ID star. Okay, so the set of players that control at least one identifier in ID star. And then for row 1, let's say in interval 0, 1, we say that ID star is a weight at least row 1 in a given execution if either, basically there exists some time slot in which those identifiers own at least a row 1 fraction of the external resources, or at least a row 1 fraction of one of the external resources, or basically there's some time slot at which those identifiers own at least a row 1 fraction of the stake. One more formula, there exists T and someone is P, with T the set of confirmed transactions of P at that time slot T, such that the stake allocation function, given the set of transactions T, allocates the identifiers in ID star at least a row 1 fraction of the total stake. Okay, so I guess the difficulty here is, as I said before, if we in the permission setting, it's easy to say that a certain set of players is at least a certain fraction of the total set of players. Right? That a set of players contains at least a third of the total number of players. Now we're in the quasi-permissionless setting, and we're considering resources, stake, and so on. Now it's not necessarily quite so simple to say that an identifier owns at least a certain fraction of the resources, right? Because things are changing over time. Okay, but this is one way we can write down such a definition. Okay, and then we say a protocol is row 1, row 2 accountable, right, the security parameter epsilon, if there exists a blame function f. Right, we're just going to have to point to guilty players in the end of consistency violation, basically. Right? So if there exists a blame function f, which maps message sets to identifier sets and satisfies the following conditions. So first of all, only Byzantine players are ever blamed. I mean, in any execution, for any subset of messages M disseminated in that execution, f of M is a possibly empty set of identifiers belonging to Byzantine players. Okay. And 2, for each protocol instance in which the adversary is row 2 bounded, the following holds with probability at least 1 minus epsilon. So if a consistency failure occurs, then there exists some finite set of disseminated messages M with f of M of weight at least row 1. Okay, so roughly then, so long as the adversary is row 2 bounded, whenever there's a consistency violation, you get to blame at least a row 1's weight of players. Okay, you get some proof that they're guilty. Okay, so now let's just sort of examine that definition a little bit. Okay, so let's note that a row resilient protocol is vacuously row 1 row accountable for all row 1, right? Because with a row bounded adversary, consistency violations can be avoided anyway. Okay, so there's nothing interesting happening in that case. Okay, so in the interesting parameter regime, then row 2 exceeds the values of row for which row resilient protocols exist. Okay, we're interested in accountability when the adversary is large enough to be able to cause consistency violations. Otherwise, it's vacuous. Yeah? So in this regime, one cannot expect row 1, row 2 accountability unless row 1 is less than or equal to row 2. Okay, so for fixed row 2, the goal is to design protocols with row 1 as close to row 2 as possible. Okay, let's have a little think about what we already know. Well, the previous proof that dynamically available protocols cannot function in partial synchrony, I've examined that proof. That implies that in the dynamically available, authenticated and partially synchronous setting, no blockchain protocol can be row 1, row 2 accountable for any row 1 greater than 0 and any row 2 greater than 0. Okay, so basically, in a dynamically available and partially synchronous setting, there's nothing you can do with accountability. Okay, how about for the synchronous setting? So in the dynamically available authenticated here just means we have a signature scheme available. Okay, so in the dynamically available authenticated and synchronous setting, the interesting case is when row 2 is greater or equal to half. Right? Because below that point, because we can just ensure there's consistency anyway. Okay, so the interesting case is when row 2 is greater or equal to half. And in that case, New, Tas, and Se have shown that accountability is not possible. Okay, and their proof is easily adapted to our framework. Okay, so we get the following result, which is basically due to New, Tas, and Se. Okay, so for every, well, you can do all the security parameters if you like. Basically, this just says that there's no zero resilient blockchain protocol that's row 1, row 2 accountable with security parameter epsilon in a dynamically available, authenticated, and synchronous setting. Okay, so in the case of dynamically available protocols, okay, there's nothing you can do in partial synchrony and nothing interesting you can do in synchrony either. Okay, we'll soon see though that in the quasi-permissionless, authenticated, and partially synchronous setting, there is a proof-of-stake blockchain protocol that's a third one accountable. Okay, so basically we have, it doesn't matter how large the adversary is, right? In the event of a consistency violation, we get to blame at least a third of the players, at least a third of the stake. Together with the previous theorem, this therefore establishes a formal separation as to what's possible in the dynamically available and quasi-permissionless settings. Okay, so basically, accountability is possible for quasi-permissionless protocols and not for dynamically available protocols. Okay, so that gives us our first separation in the next video. So that's in fact the second separation from the sequence of 3 that I listed. In the next video, we'll go on to consider optimistically responsive protocols.